Hi, we're going to keep talking about bonding, triple bonding, yay. You probably are used to this by now. This is nitrogen, nitrogen MSDS, molecular weight 28, nitrogen atomic weight 14. What? We already know this is one of the diatomics, so let's see what it looks like. I'm going to quickly draw two nitrogens. Maybe it'd be beneficial to rotate one or both of them, actually. So I'm going to rotate the electrons really quick. Don't forget that we're allowed to do that anytime we need to, right? As long as we still have three unpaired electrons, one pair on both of the nitrogens. So let's make a bond, right? The whole idea is stability, octet rule, bond there. Well, that's not good enough. If we stop there, each nitrogen would have 6 electrons. Double bond, why not? That brings us up to 7H, and oh, shocker. N2 has to exist. The only way N2 works out, while still making sure that each atom has its stable octet of electrons, is to make what we call a triple bond. So to clean this up a little bit, that would be that. And then do not forget, you always have to show 8 electrons around for a stable molecule. So 8 electrons around each atom. So there you go. Two ways to represent it. We've got either 3 lines or 6 dots. So much the same as before, everything we said. This still allows multiple to count for both atoms, so this would be 8 electrons for the nitrogen on the left, and this would be 8 electrons for the nitrogen on the right. Same with the bottom. And then, a triple bond is stronger than a double bond. A triple bond is shorter than a double bond, so longest bond is single, and strongest bond is triple. So this is all pretty much a direct extension of everything we said about double bonds. This does bring into question, all right, some new information. Why doesn't everything triple bond then? And to give a little bit of a better explanation of this, I felt the need to include some pictures. So you might be most familiar with this image here. That is the electron cloud of one of the orbitals of an atom. It's a sphere. To varying degrees in my classes, we have talked a little bit more about the other orbitals shapes that exist. It does turn out that with higher order orbitals, principal energy levels 2 and above, you get different shaped orbitals depending on how you're solving that Schrodinger equation. All I mean to say is the bond occurs when there's overlap between orbitals of 2 atoms. And they actually overlap and they mix and they become what we call a molecular orbital. In order to make a bond, you have to have a good amount of overlap, and the simple fact is that if you have a really big p orbital, a really big one of these dumbbell-shaped orbitals, my drawing is awful, the amount of overlap that you get decreases as the orbitals get bigger because the clouds get more diffuse, and it's really hard to literally get them close enough to get that good overlap. So really, this multiple bonding is a thing, but it really only happens with these period 2 elements that are nonmetals. Another question you might have. All right, we did double, we did triple. Can we do quadruple bonds? No. Don't do that. Bad idea. Now, again, a little bit fuzzy on the explanations, but like I said, when bonding happens, the orbitals actually overlap and become these molecular orbitals. But the geometry of it says that to get these triple bonds, you have to overlap all of these orbitals here. And what you're leaving is these orbitals in the back, and they just simply can't bend around to make some sort of overlap that would result in a bond. So whenever you're making these bonds, remember all the rules we had before carry through. Triple bonds are okay if needed, but don't make anything more than that. This actually does help explain why carbon isn't listed on those polyatomics. C2? No, we don't do that. And in fact, if you tried to make C2, what you'd end up with is extra electrons pointing outward, and that is why carbon in particular, carbon atoms, when they start trying to bond, when they bond with each other, will make rings and networks and long chains instead of making these discrete molecules like we see with nitrogen and oxygen. That's your reason. It just doesn't work. You can't get them to make C2. So some more examples for you to draw some molecules with. Remember our first step, draw all of the atoms with the proper number of electrons. We've got our bonding carbon. I'm rotating the nitrogen again, 5 valence electrons, 1 pair, 3 unpaired. Let me make some bonds. So there's our single, right? The hydrogen here would have its 2 valence electrons. That would be stable. But the other 2 are not, so we're going to start making more bonds. And I think now we've paired up all of our unpaired electrons. This is another checkpoint for drawing Lewis structures. 1, 4, and 5. That's 10 electrons. And we have 10 electrons showing. But the carbon has 8, the nitrogen has 8, and the hydrogen has 2. So if we were to clean that up a little bit, it would look like this. Don't forget your lone pairs. Again, we'll do the same thing here for C2H2. Remember, our general rule is to make single bonds before making any higher order multiple bonds. So I think it would be a good idea probably to connect both the hydrogens to the 2 separate carbons. If we connected both, well, you know what? Let me try. Let me try and see what happens. Let me see how I kind of pair things up, right? So we've got a bond there, and we got a bond there. So now your carbon on the right is done. So we can't do that again, right? This carbon on the left, this would be 6 electrons. That's not great. So let me clean out some of those. I'll go back to my first step. That doesn't work, and it's okay. You know, you use an eraser, you back up, you try again. Totally okay. So let's start by putting a single bond there, but then let's also connect this hydrogen to the other carbon. So now we have a straight line. I know we said in the previous one, you know, try and avoid too long of a line, but in this case we tried not doing it and it didn't work to not do this straight line. Also, we can make a double bond, we can make a triple bond. I think what you're going to end up seeing is that the most common instance of a triple bond is either going to be, you're going to use either a carbon atom, a nitrogen atom, or both. Those are really the only ones that have enough vacancies in terms of electrons in the valence shell, and they're small enough to get that orbital overlap, right? The ones below them, silicon and phosphorus, they're already too big to display a large amount of triple bonding. And then one more example to let you try. If you want to try it by yourself, you can go ahead and pause. But I'll draw out the molecules, the atoms myself to get started. All right. All right. Let's start connecting. I think from the previous example, it would be a good idea to do what we were doing before, right? So this idea of like connecting all of our carbons with a single bond, connecting to a hydrogen, and then also connecting to one on the end. Now, hypothetically, we could put the other 2 hydrogens on the right on that center carbon, but that would fill up your center carbon, and then that I don't really know 100% how the first and the third carbon would like reach each other, because we're trying not to make triangles or squares or anything. So if we're trying to avoid that, I think a better idea would be connecting the hydrogens as much as possible to the outside of your molecule, and now you're kind of freed up to make a multiple bond here and a multiple bond there. And so again, if we clean that up, what we get is something that looks like this. Kind of interesting thing out there to see. This is a molecule maybe you don't see too often. I believe it's called allene. Let me back up a bit though, because I think there's another way we could do this. Let me break that bond, and let me break up these bonds. What if instead we still wanted to keep everything? Let me change to this color. Instead of attaching this last hydrogen to the carbon on the left, could it still work if we did this? I think so, because then you could make a double bond here and a triple bond here. So to draw that one out, it would look like this. Yeah, and I think in both cases, this is C3H4. You should have 3 times 4 plus 4 is 16 total electrons. Yep. And every atom involved either has a duet or an octet going, so it's a stable configuration. I think actually in this case we have 2 potential ways to draw this chemical formula, which in a way is saying this kind of starts to talk about why for covalent bonding, sometimes just seeing a chemical formula isn't specific enough, and there's multiple ways that you can build these molecules, which is totally fine. I mean, if you ever got this in a testing situation, obviously there'd be multiple correct answers. Either one you get is still a valid Lewis dot structure. Thanks for watching.